All right, we'll give everybody a few seconds here to continue to roll in. All right, so we can go ahead and get started here today. And so, hello everyone, I'd like to welcome you to EPSP Connects. My name is Scott Feehan. I'm a PhD student at the University of Nevada. And along with my co-organizers, Adita Mukherjee, Claire Masteller, and Joel Shangros, we'd like to thank you for joining us for this installment. EPSP Connects is a monthly seminar series that alternates between wide-ranging panel discussions and scientific talks. And before we dive into our outstanding presentation today, I'd like to remind you of our upcoming events on August 19th and September 16th, with details you can see here, as well as more information on our EPSP website. And as a reminder, pre-registration is required, and we'll be sending out emails for that, and you can also do it on the website as well. A few small logistics: the chat will be disabled during the presentation, with the exception that you may directly message the organizers if you feel as if your question is pressing. We'll do our best to fit it in if at all possible. Following the talk, we'll open up the chat for questions, during which myself will field those as they come in. And so without further ado, it is my pleasure to introduce our seminar speaker today, Dr. Ken Ferrier. Ken started his academic journey at Cornell, where he received his undergraduate degree in physics. He then went on to the University of California, Berkeley, where he received his PhD in Earth and Planetary Science. Following this, he was a postdoc at MIT and later on Harvard before joining faculty at Georgia Tech, where he was appointed until 2018. Since then, he has been an assistant professor at the University of Wisconsin-Madison, and today we look forward to hearing about his most recent work in his talk titled Sediment and Soil Chemical Weathering, Transient Behavior at Source and Sink. And I'll let you take it from here, Ken.
Great, I'll go ahead and share my screen now and kick things off. Okay, everybody can see that? It looks all right. I'm gonna take all of your collective silence as a yes and just get going. Anyway, thanks to the conveners for the invitation. Really appreciate the work you've done putting this seminar series together, and I'm honored to be invited. I'd also like to thank the conveners as well as AGU's EPSP committee for their recent statements affirming a commitment to anti-racism and to diversity and inclusion in the geosciences, and specifically in geomorphology. This is hopefully the first of many steps. And hello to all of you who showed up to see this in real time. It's good to see all of you, if only remotely, and as in tiny little black boxes with your names on them. And I look forward to seeing you all again in real time, in reality, whenever that happens to be. And to those of you who happen to be watching this on YouTube in the next couple weeks or so, hello from the very recent past. So today I'm excited to tell you a little bit about what my research group has been up to recently. I've been told I've got about 40 minutes or so for this, plus questions. So in the next 39 minutes or so, I'm gonna go through a talk here which is divided into two halves, which is represented by the two halves of the screen that you see here. The first half of the talk is going to be about the connection between topographic evolution and the geophysics of sea level change. So it's going to focus a lot on what's happening near the coasts. And the second half is about the sensitivity of chemical erosion rates in soils and soil-mantled landscapes like the one that you see on the right half of the screen over here. The sensitivity particularly to the time scale of the response to tectonic and climatic perturbations. Both of these halves of the talk are going to be strongly focused on numerical modeling rather than field measurements. And while these might seem like relatively different topics, there's a common thread across them, which is that there's strong transient behavior at both ends of the source to sink system. And the real take-home message here is that relatively complicated behaviors can emerge from relatively simple forcings at both the sink and the source for sediment under relatively simple rules. All right, without further ado, we can jump right into it here. Let's see. Right, picture of me. This is not to remind you what I look like. You can see me obviously in the corner of the screen up there too, but this is just a reminder to me to let you know that everything you're about to see here was done in collaboration with a number of different people. And when that part of the story comes along, you'll see pictures of those folks too. All right, let's start out with a little bit of motivation here. There are a variety of reasons for trying to understand what drives sea level change. And one of those is the question that's at the top of the screen right here. Why is sea level change spatially non-uniform? And I really like this compilation figure here from a paper by Andrea Dutton a few years ago and others, which shows relative sea level change, that's RSL on the y-axis of each one of these little plots, over the Holocene, so from roughly 10,000 years ago to the present. And the global map in the center of the screen here is pointing out a few different locations which are highlighted in those boxes around the central map. And if you take a look at the top left corner of the screen in panel A there, you'll see that at the site in Greenland, relative sea level has been falling over the course of the Holocene, and it's fallen by more than 40 meters. It's a large change in relative sea level. But if we take a look at some other places, say just go one panel to the right of that, say go to New Jersey, you can see that sea level's been rising over the same time. It's risen by more than 20 meters. These are not errors in the measurement of sea level change. These are major geophysical changes, or differences, I should say, from one site to the next. And if we were to take a look at the other sites, you'd see that some of them have no change within uncertainties, for instance, on Christmas Island. So there are serious variations in sea level change over the span of the Holocene. And one of the key questions for us is trying to understand why that's the case, why this is the signal that we see. This is not noise. And the kind of key process that we take to this whole thing is to try to take local sea level observations. So what you're looking at here is a beautiful picture of a marine terrace on an island off the coast of Chile. I didn't take this picture, unfortunately. I've never been here to this beautiful place. This is a photo I found on Bodo Bookhagen's website, which I think illustrates what we're trying to do quite nicely. There's been a local sea level change at this site since the time that this terrace formed. It used to be up at the top of that marine terrace, and now the sea surface is several tens of meters below that. If you can date when that terrace formed or when it emerged from the sea surface, you can determine quite accurately how much sea level has changed over what time period at this site. But of course, sea level has changed by different amounts in many different places around the world. And if we want to get at how much the global water volume has changed over that time, in other words, the eustatic sea level change, the thing at the right side, the bottom of the screen over there, or equivalently the ice volume change since that time, we need to correct for a lot of different things that might have affected the elevation of this paleo sea level marker, that marine terrace, since the time it formed. And this includes a lot of different things that can perturb that. Things like ice age dynamics, things like dynamic topography, so the motion of the mantle, which makes the crust move up and down. And also the one that I focused on the most in my group, which is sediment fluxes, the erosion of large amounts of sediment off the continental surface and the deposition of large amounts of sediments into the ocean. That deforms the crust and changes the gravity field and also changes Earth's rotation axis too, all of which affect sea level changes. So it's that interpretation in the central part of this diagram, which is really important for us. And one of the key things I'd like to get across here today is that modeling those kind of sea level changes requires a model that can handle the changes in gravity that occur during sea level change. And one way to think about this is that if you were to take a large ice sheet and melt it, and you dump a bunch of water into the ocean, not only are you changing the water volume that's contained in the ocean basin, but you're also changing where the mass is on Earth's surface. You've taken some mass from here and you moved it over there, and because of that, you've changed the gravity field too. And the water conforms to whatever the gravity field is doing. But of course, the water exerts a gravitational attraction itself because it is massive. And this is the key idea behind this term, gravitationally self-consistent. You'll hear me use that term a number of times today. That's kind of the key idea behind this modeling. It needs to be gravitationally self-consistent so that the water knows where to go appropriately. So a couple key ideas behind this. We're doing a little bit of a sea level primer before we get into some results here, just to make sure we're all on the same page. Gravity matters quite a bit for sea level change. So changes in the gravity field drive changes in the sea surface. And one thought experiment that illustrates this quite nicely is this one from a paper almost 20 years ago now by Mitrovica and others in 2001. What you're looking at here is a global map of sea level change associated with a unit melting event in Greenland, so way up in the northern part of the map that we're looking at here. And the colors at the bottom of the screen, the color bar, are telling us the kind of the scaled change in sea level. The redder and oranger colors and the lighter blue colors are all places where sea level has risen as a function or in response to this melting event in Greenland. And you can see that in places that are far away from Greenland, there's been the most sea level rise, so in the South Atlantic, for instance. But the amount of sea level rise gets gradually smaller and smaller and smaller as you move up the Atlantic Ocean, and indeed as you go north in the Pacific Ocean as well. But there's a hinge point in the North Atlantic between roughly Newfoundland and Ireland, where we move into this very dark blue color. And that's a place where sea levels actually fallen in response to this melting event in Greenland. And this is in part a response to the change in the gravity field. If you were to melt all of the Greenland ice sheet, not only are you dumping a lot of water into the ocean, but you're changing the gravity field. So the water is no longer pulled up the North Atlantic nearly to the extent that it was before. And in fact, sea level would fall in Greenland as a result of this. This is known as a sea level fingerprint. So gravity matters on the one hand. Another thing that matters quite a bit is the response to the solid Earth. So we've all heard of glacial rebound or post-glacial rebound. The generic term for this is glacial isostatic adjustment. If a very large, very heavy ice sheet grows or melts, for instance, the Laurentide over North America, then the crust rebounds or depresses under that load. And this is a response that takes thousands, in certain cases, tens of thousands of years to fully respond. And even today, the relative sea level changes that we observe up and down, this is now mostly the east coast of North America here, from St. John's, Newfoundland, down into the Gulf in Galveston, Texas. This is a study from just a year ago that compiled modeled rates of sea level change at these sites. And I would just want to highlight one component of this, or one driver of that relative sea level change. That's the purple bar right at the top of each one of these bars here. That's the one that's associated with glacial isostatic adjustment. That is the ongoing crustal response to the loss of the Laurentide ice sheet thousands of years ago. And because the mantle is such a sluggish thing, because it is still not completely at equilibrium under the loss of that load, the crust is still responding, and hence sea level is still responding there too. Before I jump into some simulations here, just start with a quick definition of what I mean by sea level. And I'd like to go through this in part because I often find at the end of a talk, many of the questions I have are about what do I mean exactly by sea level. And sea level here is defined in the modeling community as the difference between the sea surface elevation. So that's the sea surface equipotential you see at the top of that little cartoon there, and the solid surface below it. And the solid surface below it is the sum of the elevation of the crust plus whatever rounded ice thickness you've got there, plus whatever sediment thickness you've got there too. And the notation we use for that is that equation we see at the bottom of the screen. So the sea level at any one point is known as SL, and it's equal to the difference between the sea surface equipotential and the elevation of the crust and the thicknesses of ice and sediment I and H. This is defined globally. So we can define this sea level field both over continents as well as in the ocean. And if you take a look at that equation, you'll see that sea level is defined as positive anywhere you have water, so anywhere you're in the ocean. And anywhere where the land surface is taller than the sea surface, you're on a continent or you're on land. So these are global fields, and this is why later on when I show you some simulations, you'll be able to see that these are global sea level fields, and what I'll be showing you. The change in sea level from one time to another is this equation down here. So if we imagine the change in sea level at any one location from one time to another time, we can simply take the difference in each one of those fields, the difference in the sea surface equipotential, difference in crustal elevation, and the changes in the ice and the sediment thickness too. That gives us the change in sea level. And I know this is a simple equation. There's just subtraction, right? This is not complicated math. But I'm belaboring this point a little bit because this is an equation that's known as the sea level equation in the literature. It's kind of a grandiose name for a pretty simple equation, but ultimately what we're doing when we model sea level changes is solving this equation. And to be a little bit more precise about it, the way that we usually do this is we prescribe changes in ice thickness, that's delta I, and changes in sediment thickness, which is delta H. And we use those as drivers for a numerical model of sea level change. And we compute the changes in the crustal elevation, delta R, and the changes in the gravity field, that's delta G, and use those to compute changes in sea level here. The kind of modern efforts to model sea level change are all built on this one classic study by Ferrier and Clark in 1976, who were the first to put together a framework that is both gravitationally self-consistent and includes a deformable viscoelastic earth underneath it. And there's been a number of kind of improvements on that model, or rather, I should say, extensions of the model, to include things like the migration of shorelines, which can account for variations, spatial variations in the water loading as sea level rises and falls, to account for earth rotation as well, sediment risk redistribution, or the combination of erosion and deposition, as well as dynamic topography. But ultimately, it's all built on this paper in 1976, which is one of those classic papers that maybe isn't read as often as it should be, but is actually quite enjoyable to read too. How do we actually do this? Well, in order to compute the Earth responses to changes in erosion and deposition, or changes in ice loading of the surface, you need a Earth model that deforms under those changes in loads. The results that I'm going to show you today are going to be simulations that were conducted on a so-called spherically symmetric Earth model. It has an elastic lithosphere of constant thickness all the way around it. It has a mantle, which is viscoelastic. It has density and elasticity profiles that are taken from PREM. It's got a viscosity profile taken from a viscosity model known as VM2. And the way we solve this is all in spherical harmonics, discretized at degree 512. This is an approach that allows you to solve these simulations on a regular laptop in a couple hours or so. So relatively efficient. Okay, that's enough preamble about how sea level modeling is done. Let's take a look at what the sea level model can actually do for you. What we're looking at here are some inputs and outputs of a given sea level simulation. At the left side of the screen, you can see an ice history here. This is an ice history taken from a model known as VM2. You can see the timeline at the top of that movie there. This is over one glacial cycle, so from about 120,000 years ago, the last interglacial, to the present day. And the intensity of that blue color is telling you how thick the ice is. You can here see kind of the growth and the decay of the major ice sheets over the last glacial cycle, so in North America and in Northern Europe. The right animation is the sea level responses to that. And the key take home here is that there are spatially variable changes in sea level that are being generated from the spatially variable changes in ice loading at the left here. And if you remember one thing from my entire talk today, it's that this is a specific example of the general principle, which is that there's no geophysical process that can produce a spatially uniform sea level change. Every process that you could possibly impose on the Earth's surface generates sea level changes that are spatially variable. In other words, there's no such thing as a perfectly eustatic or spatially variable sea level change. It always varies in space. And you can do all kinds of cool stuff with models like this. So this is an animation from Jackie Osterman showing the changes in ice cover and thickness. Those are the blue colors you see kind of growing over North America and Northern Europe here over the past roughly 400,000 years, as well as the sea level responses that are being generated from these changes in ice loading. And so you can see the shorelines migrate back and forth, but we can also do a lot of other interesting stuff with this too. And here I'd like to show you a couple of case studies here that kind of give you a flavor for what geomorphology can do for sea level change. And we'll zoom in at first on the Himalayas here and ask how much does erosion and sedimentation in some of the world's largest sediment fluxes affect sea level change? This is work that's been done with a number of collaborators. Jerry Mitrovica, who I started working on sea level with as a postdoc, Peter Cliff and Liviu Giosan. Together we worked on the Indus River Basin in the western side of India and the Arabian Sea a few years ago. And on the eastern side of the Himalayas, Amelia Winner, who's a PhD student at the University of Oregon, as well as Steve Goodbread and Celine Grawl, have been working on the Ganges-Brahmaputra system. And if we want to model sea level responses to these massive erosion and deposition fluxes, we first need to know what the patterns are like and how fast it's happening. How fast is erosion and deposition occurring? So in order to do this, the first thing that we can do is to actually dig up some empirical estimates of erosion rates and deposition rates. This is now focusing on the western half of that picture there. The gray areas on land that you see here are places where I was able to find published estimates of erosion rate measurements. And you'll see that there's some blank areas on that map there. Those are places where I wasn't able to find any erosion rate measurements, either in the present or in the past. So if you are one of those people who happens to measure erosion rates, either in the modern or paleo erosion rates, well done for you, first of all, and also please continue generating all of that incredibly valuable data. It's so useful for the kind of sea level modeling that we do. So from those kind of literature surveys, we can develop a picture about what erosion rates and deposition rates are like. That's what this map is showing us here. The blue colors are showing us erosion rates. The reddish or magenta-ish colors are showing us deposition rates. In the Indus Basin, the take-home basically is that erosion rates tend to be faster up towards the Himalayas. And deposition tends to be fastest right around the coast, around the submarine delta, as well as in the Indus Valley, or the lowest Indus Valley on land. And if we use this as a driver for sea level responses, both on the west side, and then if we combine it with Amelia's work on the east side, we can end up with sea level responses that look like this. This is now an animation, again, over roughly the last glacial cycle, so 120,000 years ago to the present, showing us the change in sea level from the beginning of the simulation cumulatively through the end of the simulation. And what you should be seeing for most of the simulation is a lot of blue. And the blue means that sea level has fallen relative to what it was at the beginning of the simulation. And the reason for that is that over these relatively short time periods, tens of thousands of years, the biggest driver of sea level change is the change in the ice volume. So as the ice caps were growing over North America and Europe, it was taking a lot of water out of the ocean. And so it was making sea level fall. But by the time we get up to the Holocene, you should be able to see these kind of red zones pop up around the northern Bay of Bengal and the northern Arabian Sea. And those are the fingerprints of sediment redistribution here. There's a lot of sediment getting deposited in those areas, and that's driving changes in crustal elevation and driving changes in the gravity field, which are driving regional variations in sea level too. And those are making sea level increase, largely because the crust is moving down and the gravity field is moving up a little bit at the same time. What I hope you take away from this animation is that the fingerprint of sediment redistribution, at least in these places which have very, very large sediment fluxes, the Ganges-Brahmaputra alone has something like 1 billion tons of sediment getting fluxed out of it every year, are non-trivial. These are significant changes in sea level. And those, according to our simulations, those perturbations on sea level change are probably continuing today. This is a snapshot of the rate of sea level change only over the last 100 years in a simulation here. And the point of this is that the rate of sea level change around the Indus Delta, is that kind of reddish hotspot there, is still several tenths of a millimeter per year, which is a significant fraction of the average rate of sea level change over the 20th century, which was a little bit more than 1 millimeter per year. It's accelerated quite a bit over the last few decades, but this is a substantial correction that we would need to account for if we wanted to interpret the drivers of modern sea level change. And the sign of this perturbation matters too. So if we were to take a look at the city of Karachi and ask, which is right very near the Indus Delta there, what is the effect of sediment redistribution on the sea level change there? we would find these figures over at the right side of the screen over here. This is a timeline of relative sea level change. This present day is at the left side of the axis there, moving backwards in time to 120,000 years ago. Running those simulations, one that includes sediment and one that doesn't. Those are the dashed lines and the solid lines there. The difference between those two lines is the figure that you see at the bottom of the screen. And the thing I'd like to point out here is the amplitude there. We have a difference between those two sea level curves that gets pretty close to about 15 meters or so by the time you get back to the last interglacial. And for someone who, at least like me, started out thinking about erosion in relatively mountainous areas, you might think that 15 meters is not that much, but it turns out to be a whole lot in the sea level world. The combined effects of melting the Greenland ice sheet and the West Antarctic ice sheet would be something like 10 meters or so equivalent of global mean sea level change. So an error that one would incur if one ignored sediment redistribution here would be larger than the combined effects of melting both of those ice sheets. So it would have a large effect on our estimates of ice sheet stability at the time. All right, one more quick review of a recent study led by Greg Rutnick, who's a postdoc at UW-Madison until quite recently, focusing on the island of Taiwan that we see here. And this is a study that was recently published in collaboration with J.C. Kreveling and Matt Fox. We zoomed in on Taiwan because it says some of the fastest erosion rates on the planet. And even though it's a relatively small island, we wanted to know how much might this very rapid erosion and deposition affect sea level changes here. Oh, right, and this is a great opportunity for me to plug Greg's AGU talk. Normally when I do this kind of thing, it's at AGU, and so I can say Greg's giving a talk tomorrow, but Greg's gonna be giving a talk in like 5 months, so put it on your calendar. It's gonna be great. You'll hear more details than the brief summary that you'll see right here. So Greg led our efforts to try to understand the erosion and deposition patterns in and around Taiwan and to compute the sea level responses to that. And Greg took a similar approach, which is to acquire empirical estimates of deposition rates and erosion rates from a number of studies, including especially Matt Fox's study from a few years ago, inverting for erosion rates on land in Taiwan. And to jump right to kind of the end of that simulation here, this is the net change in sea level associated with that very rapid erosion and very rapid deposition offshore. And what's interesting about this result relative to the results we were looking at a moment ago is that here the erosion wins out over the deposition. So unlike in the Ganges-Brahmaputra and unlike in the Indus River deltas, here the coast is so close to very rapid erosion in the coastal ranges in Taiwan that the effects of erosional unloading outweigh the effects, literally outweigh the effects of depositional loading slightly offshore. And so here, sediment redistribution makes sea level drop instead of sea level rise, like we saw there. And if we were to take a look at just one location on the coast, this little black dot on the eastern side of Taiwan that you see in the map on the left side of the screen, and ask how much does incorporating sediment redistribution matter for modeled sea level responses? This is what we see here. If we run two simulations, both driven by global ice changes, but one of them including the rapid erosion deposition and one of them not, the net effect of sediment redistribution there is to make these paleo sea level markers from the last interglacial, if they existed, increase in elevation and increase by quite a lot in elevation, well more than 100 meters or so. And we can compare these modeled sea level results to any paleo shorelines that have been dated that we might be able to find. These black dots along the east side of Taiwan are showing us some locations where there have been some dated paleo shorelines. And Taiwan's kind of an interesting case for this. It's eroding so quickly that paleo shorelines or paleo sea level markers are eroded incredibly quickly. So it's pretty difficult to find old paleo sea level markers. In fact, as far as we're aware, the only paleo sea level markers on that part of Taiwan are less than about 15 or 16,000 years old. But that's what you're looking at here. The gray bars and triangles are showing us elevations and ages of dated paleo sea level markers. And then the purple and the pink regions are showing us regions where or rather are showing us the modeled sea level histories in two simulations, one that includes sediment and one that doesn't include sediment. And the take home here is that the simulation that includes sediment brings those modeled sea level changes higher, or the relative sea level history higher. And so it gets us closer to explaining some of the variance in the dated paleo sea level markers in this area. Not all the way, but some of the way. And we can use that to compute for rock uplift driven by sediment redistribution here. And that's what we're looking at here. This is now a latitudinal profile from south to north. And the gray dots here are rock uplift rates that would be inferred from those paleo sea level markers if we were to model sea level changes only with the global ice load changes. But if we account for the regional sediment redistribution too, we can see that those inferred rock uplift rates drop down a little bit. And so the residual rock uplift that's not driven by the sediment redistribution are somewhat lower than that. This is an analogous approach to what was J.C. Creveling did several years ago, back in 2015 in North America. And that brings me to my final point about sea level change here, which is that sediment plays a larger and larger role in driving sea level changes if you look over longer and longer timescales. The upper figure here is the famous Dello 18 curve over much of the Quaternary, showing us the movement of water into ice caps and back into the ocean and over and over and over again. Sediment, unlike water, doesn't move back and forth onto the continent and into the ocean over and over and over again. It's more or less a monotonic process. And so the sea level responses to that sediment redistribution are more or less monotonic as well. And these grow larger and larger and larger over time. So if we were trying to understand paleo sea level changes in the very distant past, the effects of sediment redistribution get proportionally larger. All right, so to briefly sum up the sea level part of the story here is that sediment redistribution can strongly affect sea level, and it can both make it increase and can make it decrease regionally. This is a process that leads to some relatively rich behavior here. So these geophysical effects are needed to account for a number of different things. So for instance, the controls on modern sea level changes, the geomorphic responses to climate change, which is something that many of us in this talk, or many of us in the audience might care quite a bit about, as well as paleoclimate estimates for ice sheet stability too. This might be an important correction that we need to make. And one of the other take-homes here is that in order to do this endeavor properly, we really need estimates of erosion and deposition rates, both at the present and in the past. All right, and with that, I will now take a sharp right turn and move into the second part of the talk. We're going to go from the sink to the source of the sediment here. And this is motivated in part by the understanding that sea level changes can drive spatially and temporally variable perturbations to the most important boundary condition for landscape evolution. And here we're going to ask the question, how do these transient changes in the boundary conditions, so for instance, a tectonic perturbation or a climatic perturbation, how does this affect the chemical erosion rates, the solute fluxes that are coming out of the very tips of a catchment? And our focus here is going to be up in the very first order basins at the tops of these catchments. And this is work that has recently been accepted in collaboration with Taylor Perrone, that you see at the bottom of the screen there. All right, so why do we care about chemical erosion? Well, I like showing a picture of a grizzly bear here because I think this picture illustrates a number of different things that chemical erosion matters for. It matters for the nutrients in the soils and in the streams that feed the fish, that feed the bears. It matters for the evolution of topography. There's a coupling between physical erosion rates and chemical erosion rates. It matters for the hydrology. It matters for the partitioning of surface water flow versus groundwater flow. Through the drawdown of CO2 from the atmosphere, silicate weathering can affect climate over long timescales too. And then to draw back to the first part of the talk, it matters for sea level as well. In addition to that, another motivation for trying to understand how transients propagate through chemical erosion rates in landscapes, is that we now know that there's abundant evidence for topographic transients too. This is a figure from a paper that I was not involved with, Easton et al., 2017. I'm merely a fan of this paper. And incidentally, please go see Helen's talk in a couple months in the EPSP Connect series. We now know from metrics like the chi metric that there are fingerprints that can be left in the topography that can reveal what direction divides might be migrating. And this is a picture that shows us that transients can last a very long time, even in the first order basins at the top of drainage networks. Our approach here was to apply a relatively simple numerical model, or rather to develop a simple numerical model that couples both landscape evolution and chemical weathering in soils. And if I were to draw your attention to the left side of the screen over there, this is kind of our hypothetical little hill slope here. This is all soil mantled. In the center, you can see these lines that are kind of moving up from each edge. You can think of those as first order channels that are fixed in space in this little synthetic landscape. And we model the chemical weathering, or the chemical weathering fluxes that are just in a well-mixed layer of soil. So we're not accounting for any chemical weathering that might be happening below the soil here. This is strictly a soil chemical weathering model. And the soil moves downhill at the same time as well. So this model is then able to model the evolution of topography, but also the evolution of soil chemistry and the chemical weathering fluxes that are leaving the soil at the same time. I won't belabor the math too much here, but there are a few processes that we're parameterizing, one of which is the dissolution of mineral phases in the soil. You don't need to memorize all of these different notations here. We also put in a linear soil transport law to let the soil flux downhill. We apply an exponential soil production rule for the conversion of bedrock into soil, which happens everywhere in the landscape. And we apply a few boundary conditions and initial conditions. So we apply a rock uplift rate field, which is uniform in space, a uniform bedrock lithology. We also impose a hill slope scale. And we'll see that this turns out to be a rather important quantity for us. That hill slope scale is that capital L that you see in that diagram. And we're going to make a few simplifications right from the get-go, one of which is that the channel network remains stationary. So those first order channels that you see coming into this hill slope are perfectly stationary in space and time. And in addition to that, we're going to assume that the soil is vertically well mixed. And that is an important simplification for us because it means we can treat this as essentially a well-mixed batch reactor. We don't need to worry about vertical variations in soil chemical weathering. And I know a little bit more math, and then we'll get on to some simulations here. This is the kind of the master equation that we use to compute chemical erosion rates. And I know I said don't worry about the notation, you don't need to memorize everything, but I will ask you to memorize one piece of notation, and that's the capital W at the left side of the screen here. That's the notation we're using for the chemical erosion rate in the soil. Remember that one, it's going to come up several times. The way we use, or the way we compute chemical erosion rate is as the product of the soil thickness and this term in the summation here, which is the sum of the dissolution rates of all of the different mineral phases that we use. And then we subtract the soil, or rather the clay production rates of all the different secondary minerals that happen to be produced here. And I bring this up largely to show that topography doesn't directly affect anything in this equation. So there's no direct coupling between topographic gradients or curvature and the chemical erosion rates. So if we want to model the coevolution of topography and soil chemical weathering, we need to go after the things that do respond to topography. And that in this model are soil thickness, H, as well as the abundance of soluble minerals in the soil. That's that capital C sub S, sub JS. And just a little bit more math. In order to simplify our interpretations of the simulations I'm about to show you, we simplify things a little bit further. So we apply a highly simplified bedrock lithology. We're going to imagine this has only two mineral phases, one of which is soluble, so you might think plagioclase, and one of which is totally insoluble, like zircon. And we're going to make it a super simple bedrock lithology. It's 50% plagioclase and 50% zircon. bring this up because my wife is an isotope geochemist who does a lot of work on zircon, uranium, lead geochronology, and it drives her crazy when I talk about bedrock that is 50% zircon. But nonetheless, it really helps us understand what kind of dynamics are going on in this model. So we're going to make it simple, regardless of the reality of bedrock lithologies like that. In addition to that, we're able to non-dimensionalize this model a little bit, to zoom in a little bit on the quantities that might really matter for the dynamics here. And I've highlighted just 3 of those here, which I've called an uplift and dissolution for a given mineral phase X and N soil. And you can think of these as just scaled versions of the rock uplift rate, the mineral dissolution rate, and the soil production rate. These are 3 quantities that may affect chemical erosion rate responses in transient scenarios. Okay, now we can get on to some simulations. Pop quiz for all of you. This is worth 0 points, but just think to yourself, if we were to take our little synthetic hill slope here and apply a step increase, an instantaneous increase in rock uplift rates, do you expect rock uplift, or do you expect chemical erosion rates to go up or go down? Now that you've all answered that to yourselves satisfactorily, let's take a look at what the simulation is actually showing us. So what you'll see here is a change in color moving across the landscape. Gray is a color that you see right now that's indicating the initial steady state that this soil-mantled landscape is in. Red means that chemical erosion rates will have gone up since the beginning of the simulations, and blue will mean that chemical erosion rates have gone down since the beginning of the simulation. And here's what we see. We see a non-monotonic response in chemical erosion rates. The timeline at the top of that little animation there is going roughly 200,000 years in this simulation. What we see is an initial drop in chemical erosion rates, followed by kind of this spatially variable wave of an increase in chemical erosion rates that migrates across this landscape. Kind of unusual. So if we were to ask, do chemical erosion rates go up or do they go down? The answer would be yes, it does both. And the reason for this spatially variable non-monotonic response is that the chemical erosion rate is really a product of 2 different competing responses. And that's what these 3 animations are trying to show. So the left animation is showing us the chemical erosion rates, the same animation we saw a moment ago. And the 2 other simulations, or 2 other animations, are showing us the change in soil thickness and the change in the soluble mineral abundance. The soil thickness has dropped, that's the blue color, but plagioclase abundances have gone up. And if we allow this to go all the way to steady state in the future, ultimately the chemical erosion rates go to a slightly higher value than they did before, but the soil thickness responds faster than the plagioclase abundances do. And so the initial response here is a drop in chemical erosion rates, followed ultimately by the plagioclase abundance increase and then the chemical erosion rate increase. This is not a universal behavior either. And this is a slide with a few different animations on it, so we're going to take a little bit of time for this one here. What you're looking at in this graph in the top right corner of the screen is the plot of steady state chemical erosion rates as a function of rock uplift rate. So if we were not to run this as a transient simulation at all, but just to ask what happens at steady rock uplift rates, this is the chemical erosion rate response to that. And you can see that there's kind of a humped relationship here. It's relatively slow at low rock uplift rates. It's relatively slow at high rock uplift rates, but there's an intermediate value in the middle, which is kind of a Goldilocks scenario where chemical erosion rates are as fast as possible. And the reason for the steady state behavior is that when we go to very slow rock uplift rates, we get very thick soils, but the soluble mineral abundances have dropped way down. So even though there's a lot of soil, there's not much stuff there to weather. And if we go to very fast rock uplift rates, the soil gets very thin, it's very chemically fresh, so it's easy to weather it, but there's just not that much soil there to weather. And so chemical erosion rates go down there. And so there's kind of a happy medium in between where you've got some soil thickness and some soluble minerals. All right, let's take a look and see what happens in the transient case now. What happens if we start with an initial condition right over here, some steady state landscape with a low rock uplift rate. And what happens if we kick it up a little bit? What if we instantaneously increase rock uplift rates by 50%? What happens then? In this case, we would get a monotonic increase in chemical erosion rates. You can kind of see this wave propagating through the landscape over in the bottom left corner of the screen, but chemical erosion rates are going up uniformly. And what happens if we would do another thought experiment? What if we were to start at a different initial condition on the other side of the peak and the steady state relationship, and also impose a 50% kick in rock uplift rates there? What would happen then? Well, then chemical erosion rates would decrease rather than increasing, but we'd still get the same monotonic response. Here it's decreasing everywhere across the landscape, and there's a propagating wave that moves across it. And right in the middle, if you cross from one side of the peak to the other, this is where we get variable responses, kind of like the ones that we saw in the previous slide, where there's this spatially variable non-monotonic response in chemical erosion rates. The take home is that there's some relatively complex behavior that results just from the form of this steady state relationship and where that initial condition happens to be when you start this perturbation. Now we can do a couple other real quick thought experiments with a model like this too. So we can imagine doing both a tectonic perturbation and a climatic perturbation. The one at the left side of the screen here is a simulation for a tectonic perturbation. This is the same 50% increase in rock uplift rates that we saw on the previous slides. We could also imagine doing a hypothetical climatic perturbation. Let's imagine that instead of kicking rock uplift rates, let's imagine that we kicked up rainfall rates uniformly across the landscape. And we can, to keep things simple, we can imagine that a few different parameters might respond linearly to that increase in precipitation rate. So the soil transport efficiency, D, might increase by 50% as well. The mineral dissolution rate might increase by 50% as well, and the soil production rate might increase by 50% as well. Now here we see a very different response. The topography, for one, is dropping, but the chemical erosion rates have increased uniformly across the landscape as well. That's largely a function of the instantaneous increase in the chemical erosion, or rather in the dissolution rate of the soluble mineral phase there. But you can also see that there's a propagating wave that makes its way through the landscape too. And the take home here is that there are qualitatively different responses in space and in time between this very simple tectonic perturbation and a very simple climatic perturbation. To break it down in a static image here, we've got the timeline now looking at the tectonic perturbation in the top row and climatic perturbation in the bottom row. Initially, the tectonic perturbation generates a wave in chemical erosion rates that starts at the boundary and then migrates inwards. And it starts by dropping and then gradually increasing. The climatic perturbation, by contrast, doesn't just start at the boundaries. It occurs everywhere uniformly, and then there's a propagating wave that makes its way in here. These are distinct signatures, things that we might go looking for in nature as well. And then the last characteristic from simulations like this that I'd like to draw your attention to is the response time. How long does it take landscapes to respond to a perturbation like this? And for this, it'll be useful to consider the concept of the lag time or the response time. And operationally, we'll define this as the time it takes for chemical erosion rates to get 95% of the way to its final steady state value after a perturbation. One of the most important components that comes out of simulations like this is that the scale matters a lot here. The length scale specifically of the hillslope matters quite a bit. What we find is that the time it takes for chemical erosion rates to respond throughout a basin primarily depends on this so-called tau W, so the response time of W, which scales as the basin length squared divided by the soil transport efficiency. So this has a lot to do with how quickly the topography itself evolves. The topography is driving the response time of the chemical erosion rates. This is a quantity, so basin scale is a quantity that varies quite a lot in nature by multiple orders of magnitude. There's a study by Perron and others back in 2009, which showed this quite nicely, showing that the characteristic basin scale of these first order ridges and valleys tends to scale with the ratio between that soil transport efficiency, D, and the river incision efficiency, K. raised to a constant power. That implies that the scale of one of these first-order basins may be largely set by the relative efficiencies of soil transport and river incision in their first-order valleys. And that in turn implies that the response time should be sensitive to the efficiencies of river incision and soil transport. These might matter a lot. And this is, I would say again, one of the key take-homes of this study is that the ways in which that climate and rock type and biota might influence the response time of chemical erosion rates in these first-order basins might mostly be due to their effects on the efficiency of either river incision or on soil transport. The reason I'm focusing so much on that basin scale there is what you'll see in the next few slides here, which is that these other effects, these other non-dimensional numbers appear to not matter nearly as much. So if we were to take a look at the response time of W right at the peak of that hill slope, as a function of the scaled rock uplift rate, so the N uplift number on the x-axis here, we can see that it does vary somewhat. It varies by maybe a factor of 3 or 4 or so, but that is much, much smaller than the variation in the response time of chemical erosion rates that we saw on the previous slide as a function of just how big the basin is. How about rock type? What if we were to compare the first order basin in a granitic landscape like the one we see at the left here to a basaltic landscape like the one we see at the right? This is now kind of a busy graph here, but we're plotting the response time as a color, that's the color bar at the right side of the screen there, as a function of the two other non-dimensional numbers that I pointed out a while ago, one of which is the scaled soil production efficiency that's on the x-axis here, and one of which is the scaled mineral dissolution efficiency, which is on the y-axis here. And there is some dependence on each one of these non-dimensional quantities, but mostly we see that these variations are only about a factor of 2 to 2.5 or so. They're just not that sensitive, or the response time is just not that sensitive to either the soil production efficiency or the dissolution efficiency. It's mostly a function of how big the basins are. And to put some numbers on this, the modeled response times for chemical erosion rates vary within a basin, but they're typically around 10 to maybe 1,000 years, or 0.01 to 1 million years for typical basin sizes and typical soil transport efficiencies. And that's a time scale that is comparable to the response times of fluvial networks themselves. And what this means is that if you were to go all the way down to the sink, if you were to go to a sedimentary deposit, the response time that you might infer from a sedimentary record might be largely driven by the responses of these first order little basins right at the tips of the valley networks. All right, and now I finally am on my last slide here. Couple take-home messages from the second half of the talk. These climatic and tectonic perturbations can produce distinct patterns in chemical erosion rate, both in the patterns that we might see in space in hill slopes, but also the transient signatures we might see in deposited sediment. So this might help us interpret those spatial and temporal patterns that we see. And the response time of chemical erosion rates is mostly driven by basin scale. It is modulated by these other factors like rock uplift, dissolution, soil production, but this implies potentially a key role for the factors like biota or climate or rock type on the efficiencies of river incision and soil transport. And I think to move forward with this, what we really need are some great test bed scenarios. So places where we have excellent measurements of chemical erosion rates over time and rock uplift rates, soil production, soil transport, and river incision in landscapes that are responding transiently. And with that, I've come to the end of my slides, and I will be happy to take any questions that you have.
Okay, awesome. Thanks, Ken, so much. The chat is now open, everyone, so you can enter your questions in there. Take a minute or two to do that, and then Scott and I will moderate a quick question session. So Ken, while we wait for the questions to come in, really excellent talk. Thank you so much. Thinking about taking both sides, the source and the sink, together, can you talk about maybe how those perturbations, both at the upper edges of the source and the sink, might interact with each other
Right, great question. There's been so much great work over the past couple decades about how signals from the source can be modified between the source and the sink, you know, the environmental shredding that river networks are so good at doing. Right, well, I think the degree to which that signal might be transmitted from the source to the sink depends probably in large part on basin scale. How big are the channel networks through which these signals might be propagating? One might imagine kind of the ideal scenario for, you know, kind of retrieving a source signal might be a tiny little basin where you have a first order basin that's depositing sediment into a deposit that's very close to that first order basin itself. So that's a kind of an arm wavy way of saying I think it depends probably on the basin itself. Good question. I think you might be muted, Claire.
Yes, I've got it. So does anybody else have any questions? Please enter them in the chat or raise your hand and we can try and call on you. All right, so there's a question now in the chat from Paul Richardson. Paul asks, the landscape on the left shows striking aspect-dependent differences in microclimates. How might you use these differences to test your ideas?
Great idea. Well, I guess, again, to make this as idealized as possible, let's imagine that you have small lakes that are collecting deposits on each side of that asymmetric topography on the left side there. The climatic effects on each side of that ridge, you might imagine affecting several of the parameters in this relatively simple model. So it might affect the soil transport efficiency, and indeed there's already great empirical evidence showing that climatic variations, microclimatic variations on either side of a ridge can affect soil transport efficiency. So for instance, Nikki West's work in the Shale Hills CZO. So that parameter might be strongly affected. One can easily imagine chemical erosion efficiency being affected there too. So the way it's parameterized here, the dissolution rate constant or the kinetic rate constant being affected as well. So we might expect the soil chemistry to vary on that hill slope on one side of the ridge relative to that on the other side of the ridge too. And that's something that you could test by, you know, walking around on that landscape. Instead of looking for deposits that might give you a sense of the time history in sediments or in sediment cores, you might be able to actually just do this by hiking around on that landscape, collecting a bunch of soils on the right side of that ridge and a bunch of soils on the left side of the ridge. This is another thing that this relatively simple model predicts, is spatial variations in soil chemistry. From a modeling perspective, that'd be relatively straightforward to impose on the model. We could impose a different, you know, rainfall rate on one side of a ridge than on the other side of the ridge. As you know, that would generate not just variations in soil chemistry, but it would also generate variations in topographic asymmetry too. Yes, that'd be a fun experiment to do.
So unmuting myself here. We've got a question from Shenliang Wu. Hopefully I said that correctly. Is there a threshold in the change of environmental forcing, example, climate and uplift, that will override the impact of basin scale?
Good question. Is there a threshold in rock uplift rates that would override basin scale? Not within the context of the numerical model that we've got. I think we kicked this model quite hard in terms of the rock uplift rates that we imposed upon it. And there are upper and lower bounds on the rock uplift rates that can be imposed here. At the lower bound, it's 0. So we could impose no rock uplift on this at all, in which case the landscape would just kind of diffuse away. And at the upper end, the maximum rock uplift rate that we can impose on a model like this is constrained by the soil production rate constant. So in this model, we are computing soil chemical erosion rates, which means that there has to be soil on the landscape in order to weather. If we drive the model with a rock uplift rate that's higher than the maximum possible soil production rate, then the soil disappears, and there's no chemical erosion at all in the landscape. And in the kind of sensitivity analyses we did, we pushed it up pretty close to that maximum rock uplift rate before the soil completely disappeared. So at least within the context of this model, I don't think that there is a threshold rock uplift rate that could overwhelm the importance of basin scale. Good question.
Okay, there's another question from Alexander Sims. He says, Ken, nice talk. Thank you for sharing your interesting work. Regarding the study from Taiwan suggesting very high rates of uplift due to erosion, I noticed you used a lithospheric thickness of 10 kilometers, which is on the thin side of most GIA models. How sensitive are your results to lithospheric thickness?
I'm so glad you asked that question. This is something I breezed right by in the first half of the talk in the interest of trying to get everything done on time. We did a little bit of sensitivity analysis in that study. So the Rutnick et al. 2020 paper also examined, or rather also ran a simulation with a lithospheric thickness of 30 kilometers. We chose those values because those appear to be roughly the range of lithospheric thicknesses that are appropriate, or elastic lithospheric thicknesses that are appropriate for that region. But you're right, in many of these sea level simulations or GIA simulations, these are being applied to places where the effective elastic lithospheric thickness is quite a lot thicker than that, even an order of magnitude thicker than that. And so I myself was a little bit surprised to find that the thicknesses were as small as they were there, but evidently that's what the geophysicists are telling us there. To get to the kind of a second part of your question there, what effect would a thicker elastic lithosphere have on the sea level responses? Well, what we found is that if we run this with a 30-kilometer elastic lithosphere instead of a 10-kilometer elastic lithosphere, we find that these signals are generated over a wider wavelength, right? So these crustal perturbations are expressed over many tens of kilometers wider distance than they are in the thinner elastic lithosphere case. That turns out to be most important for so there are a few little islands that have some paleo sea level markers, which are tens of kilometers off the eastern shore of Taiwan. And those are particularly sensitive in the model simulations to the chosen effective elastic lithospheric thickness.
And we are running right up on the hour now. So if anybody has any last questions, you can throw a quick message in there saying you're still typing, or if nobody else has any questions, yeah, I'd like to thank Ken for the amazing talk today. It was really good. Wish we could all give you a round of applause. And I'd just like to thank everybody again for tuning in this installment. Just remind everybody we have an event coming up on August 19th, Productive Work Habits in Grad School and Beyond. And hope to see you all there. Ken, again, thank you so much. And thanks everybody else.
Thank you.
Thanks, guys.
Take care.